So our last trend for today is ionization energy. Ionization energy, just think of it, how much energy does it take to remove an electron? If it takes more energy to remove an electron, you need a high ionization, it means it's held tightly. So the more tightly an electron is held, the more the ionization energy. The more loosely an electron is held, the lower the ionization energy. So the amount of energy required to remove an electron from the ground state of a gaseous atom or ion is called ionization energy. First ionization energy is what's required to remove the first electron. And then the second ionization energy is that required to remove this second electron. So let's look at an example. We're going to look at successive ionization energy. So what we're going to do is keep moving electrons from the same atom. One thing that would be helpful in this is to look at the electron configuration. We're going to look at the electron configuration of aluminum. Aluminum's configuration is 1s2, 2s2, 2p6, 3s2, 3p1. Now one thing you want to be able to note here, what are the core and what are the valence electrons? Notice all these are core electrons, and then these electrons, I'm going to circle these, are valence electrons. Valence electrons are always further away and a higher energy. Remember, when you do electron configuration in this order, it's order of increasing energy. The higher the energy of the electron, wherever the orbital is, the easier it is to remove that. If you look at the first ionization energy of aluminum, you remove one electron, so you end up with Al+, and that's how much energy it takes to remove an electron from a mole of aluminum. But removing that second electron, so if we take Al+ again down here, and then remove another electron, we're going to end up with Al2+. Now this is larger for two reasons. First of all, the first one was lower because you're removing from a 3p, which is further away and of higher energy. Now we're moving from a 3s, which is of lower energy, and also you're removing the electron from a positively charged Al+. Let's do it again. Remove another electron. You're going to be removing this time that other electron that's in the 3s2. Now that will be the end of the electrons in 3s2. This one's even higher because once again it's positively charged, and you're removing it from a s orbital. Now next, if you removed this fourth electron, there's a huge increase in ionization energy. Why is this so big? Well, the reason being is you're removing this 2p6 electron. You're going to be removing one of those electrons. That is a core electron. And each time you remove an electron from the core, it's going to be a huge increase in ionization energy. Why? Well, for one thing, that electron is much closer to the nucleus. Remember, if it's closer to the nucleus, there's a greater pull, higher ionization energy to remove that electron. Ionization energies, if we look at the chart, it requires more energy to remove each successive ionization electron, and if you look at a series, and when all valence electrons have been removed, the ionization energy shows a huge increase when you start to remove those core electrons. The huge increase is, notice sodium only has one valence electron, so there's a big difference going from there. Magnesium, the third one would be removing valence. With aluminum, the fourth one would be removing a core. I'm sorry, with magnesium, the third one would be removing a core electron. The other thing I'd like you to notice here is, remember, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, and argon are all in the same period. Now, what do you notice? Ionization energy increases as we go across that period. Now, why does it increase? It increases because of effective nuclear charge. As you go across that period, you're adding another proton, another proton, another proton. And those electrons that are added don't provide any shielding. And so those electrons are pulled closer and tighter and tighter. And for that reason, you have a lot greater ionization energy for argon than you do for sodium. And that's why sodium easily loses an electron. Ionization energies, there's generally two trends. The ionization energy increases when you go, if you look at all these, are in the same period. So generally ionization energy increases as you go to the right of a period. And also notice neon, argon, krypton, xenon, all are in the same column. Ionization energy decreases as you go down the column because those electrons, as you go down the column, are further and further away from the nucleus, so it's not as easy for it to pull it in close. The trends in first ionization energy, there are unfortunately two apparent discontinuities. And what that means is, generally we say ionization energy increases as you go to the right. There's two times when that doesn't. One is when you're going from family 2A to family 3A. 3A is actually lower, because what happens, that electron in 3A is actually one of the first ones in a p orbital, and those electrons that are paired in the s orbital prior to that actually provide a fair amount of shielding, and so it's actually easier to remove an electron from a 3A orbital than a 2A orbital. For example, it'd be easier to remove one electron from boron than it would be to remove one electron from beryllium. Beryllium's in 2A, boron's in 3A. And then the other discontinuity. And so that first discontinuity you see in these circles that are drawn here. That would be beryllium and boron, and these would be all the same things that are in the families as you go down those two rows on the periodic table, or two columns in the periodic table. The next discontinuity is found between 5A and 6A. Normally you'd expect 6A to have a higher ionization energy, but like 3A, it is lower. So both of these have lower ionization energies than we expect. Now the reason these ionization energies are lower for this one is because 6A, the electron is being removed from a paired p orbital, which means there's two electrons in there, in that orbital. If there's two electrons in that orbital, it's actually easier to pull one of those electrons out because it feels a little bit of repulsion. We're going to look at a question here. Which of the following atoms would have the highest ionization energy? So I think it's best to try and locate these in the periodic table. So let's look. We have silicon, we have aluminum, we have oxygen, we have nitrogen, and we have carbon. So which one is going to be, which electron out of all these is going to be held in the tightest? And the one that's loose is going to have a low ionization energy. If it's tight, it's going to have a high ionization energy. Well, first, remember ionization energy increases as you go this way in the periodic table because these atoms are closer, or these electrons are closer to the nucleus. For this reason, these, if you look at aluminum and silicon, these are actually what we call, this would be a 3p, and these right here are called 2p. Notice that 3p is further from the nucleus, and since these are further away, I'm going to go ahead and eliminate these two. If they're further from the nucleus, it's going to take less energy than the electrons that are closer to the nucleus. So that means we're going to choose between these three. Now, if you remember, ionization energy also generally increases as we go to the right. So if you just go by that trend alone, you'd probably want to pick oxygen. But hopefully you remember that there's a discontinuity between 5A and 6A. Now, why is that? I try to provide you with a visualization. If you looked at the way the orbital diagram is, here we have, if you removed an electron from oxygen, it'd be removed from this paired orbital right here. If you removed it from nitrogen, it would be from a single orbital. It is easier to remove an electron from a paired orbital because that other electron that's in that orbital offers some repulsion. So for that reason, the highest ionization energy here is not oxygen because it's in a paired orbital. Instead, it is nitrogen. Nitrogen has the highest ionization energy of anything in that column, or I'm sorry, in that row, and it's also higher than the ones in the row below it. So the correct answer for this would be nitrogen. Nitrogen has the highest ionization energy of those four. So last, we also want to look at, here's a list of ionization energy for noble gases and alkali metals. Notice the ionization energy decreases as you go down for the alkali metals. The reason being those electrons are further and further away from the nucleus, which also reminds us why the reactivity of these atoms increases. We know that sodium is more reactive than lithium, and potassium is more reactive than sodium. And so ionization energy parallels the reactivity of those alkali metals. Now let's look at the ionization energy of the noble gases. Ionization energy decreases as we go down the column. The reason being those electrons in radon are much further away from that positive nucleus than those electrons in helium. Notice in helium it's a very short distance in comparison, and so those electrons are held much tighter, has a much higher ionization energy. So the last thing we'll do is sum up our two trends that we talked about. First, let's do ionization energy. Remember we said ionization energy increases as you go to the right because you're increasing effective nuclear charge. Ionization energy increases as you go up the column on a periodic table. So this is for ionization energy. Ionization energy increases as you go up the column because those electrons are closer and closer and closer to the nucleus, which pulls it in tighter. Pulled in tighter, it has a greater ionization energy. Next, atomic radius. We saw that atomic radius or size increases as you go down a column. The reason that increase occurs is because every time you go down a row in the periodic table, you're adding a new orbital. And every new orbital is bigger and further away from the nucleus. So as you go down a column periodic table, the atoms are bigger because you're adding new energy levels. Another trend in size, remember atoms actually get smaller when you go to the right because we're increasing effective nuclear charge. So size actually increases as we go to the left. So we put size here, the biggest atoms would be the ones, like if you compare this for example, this column right here with potassium, we expect potassium to be the biggest. So size is the biggest going to the left and is larger going down. That's a quick summary of ionization energy and atomic radius. Let me know if you have any questions. I'll see you in class.